In this video, we're going to take a look at the integral test and a couple of comparison tests. Now, the goal is to deal with an infinite series. We want to figure out a couple of easy ways to find out if the infinite series that we're dealing with is going to converge to a number or if it's going to diverge. And I don't want to find the partial sums like we did in the previous video, because sometimes it takes a really, really long time to work out what the partial sums are actually doing. So we want an easy way to figure out if a series converges or if that infinite series diverges. The first test we're going to be using is the integral test. Basically, this says if we have a function which is positive and continuous and decreasing over the real numbers, and the terms of the infinite series are given to me by plugging in positive integer values into my function, then the infinite series and the integration from 1 to infinity of f of x dx are either going to both diverge or both converge. Now, it's important to point out if they do both converge, they may not, and probably won't, converge to the same number. So if I can find that the integration of some f of x comes out to 2, that does not mean that the infinite series is going to add up to 2. But what this says is if I have an infinite series where my terms are essentially given by a sequence where the function is positive, continuous, decreasing, then the infinite series and the integration are both going to converge or both going to diverge. That means if I want to find whether this infinite series is going to diverge or converge, I can calculate this integral. If the integral converges, I know the series will converge. If the integral diverges, I know the series will diverge. Again, if it does converge, it won't be to the same number. Now, let's think about why this would be. We'll look at the graphical reason for the integral test. So what I've done is I've graphed the function 1 over x squared. Now, let's pretend we are looking at an infinite series of 1 over n squared. Then each term would be a y value here. So the y values are giving me the height of each of these points. If I wanted to find the total area, or the total sum of 1 over n squared, I could add up all of the heights of that point. Now, conveniently, if I look at this set of rectangles, this set of rectangles has height exactly equal to the y value of each point that I'm adding up, the y values that I'm adding up. And it has, so height is the y value, and the width is always 1. So that means the area of each of these rectangles is the same as the height of the point. Notice that these rectangles, all except for this very first one, well, are under the curve between 1 and infinity. All of them are between 0 and infinity, but they're all underneath this curve. So this area is going to be bigger. The area under the curve is going to be bigger than all of these rectangles combined, except for this first one, which we can see has an area of 1. But the other ones are all going to be underneath the curve. That means the area of this curve, if it converges, excuse me, if the integral converges, the integral gives me the area under the curve. So if the integral converges, then all of those rectangles are going to add up to a finite number because this area in red is also finite. And the orange rectangles were all smaller, again, except for we're adding this one at the end. Now, on the other hand, I drew the rectangles where they were going left. If I drew them where they were going right, so the rectangles go this way, again, height is equal to the point, width is equal to 1 on each rectangle. Well, these rectangles are all above the curve. Therefore, if the area under the curve is infinite, then these rectangles would add up to infinity. So if we integrate, integration gives me the area under this curve. If I draw the rectangles one way, I can see that all but one rectangle is under the curve. Therefore, we have a finite area if my integration is finite. With the other way I draw it, you can see that if the integration is infinite, since the green rectangles are going to have more area, then the integration being infinite is going to force the green summation of the green rectangles to be infinite. So if the area under the curve is finite, then the infinite sum is going to be finite. If the area under the curve is infinite, then the sum will also be infinite. And we get that not just on 1 over x squared, but whatever we choose as our function. If I chose 1 over x, the same phenomenon happens. 1 over, x plus 1, the same phenomenon happens. That on one side, we get rectangles under the curve. If I draw it the other way, I get rectangles above the curve. That's, by the way, why in our statement of the integral test, we wanted to have our function be decreasing and continuous so that I could say that about the rectangles, that drawing them one side gets you under, drawing on the other side gets us above. So as long as we have positive, continuous, and decreasing function, then we can utilize the integral test. Both of these converge or both of those diverge, depending on each other. So if I want to figure out whether the infinite series converges or diverges, I check the integration. That's once again the picture. Let's do an example where we can determine the convergence of an infinite series using the integral test. Here is example 1, where we have an infinite sum, n equals 1 to infinity, of n over n squared plus 4. We'll go ahead and utilize the integral test. The first thing that I do is I create a function that gives me the terms in this infinite series, so the terms that I'm adding up. And the function, if I use x as my variable, would simply be x over x squared plus 4. That's a continuous function, and if you check it, it is decreasing and continuous and positive for n from 1 to infinity. So it's decreasing, positive, and continuous. So we can use the integral test. And basically what I do is I integrate this function from 1 to infinity with respect to x, if x is the variable I'm using. Now, you can do this in a lot of different ways. You can do this by hand. You can use substitution. You can actually take definite integrals and just use bigger and bigger points up top. In other words, you could put a arbitrary large value in there and see what happens. I will do this by hand. By hand causes us to use a u substitution. U would be equal to x squared plus 4. And then my differential exchange, derivative of u with respect to x, would be 2x. That means my differential exchange du would equal 2x dx. I'd probably divide by both sides by 2, so I'd have that differential exchange. So now when I substitute, my integration would be, I'd have this x dx changes into 1/2 du, and x squared plus 4 changes into u. So I got 1/2 times 1 over u du. Now the bounds with respect to u, if x goes from 1 to infinity, then u actually goes from 5 to infinity. That's not important, at least not at this point. So in any case, I get 1/2 times the natural log of u. I would be plugging in 5 out to infinity if I'm going to plug in u values. Or when I rewrite that, I'd probably use x values. So when I back substitute, I get natural log of x squared plus 4. By the way, I'm not writing the absolute value here because I don't need to. All of my values that I plug in are going to be positive. But when we plug in infinity, in air quotes, again, that means taking the limit as x goes to infinity, then natural log of numbers that get really, really big will also get really, really big. So we'll get infinity. And then when I plug in 1 into this, I get 1/2 times natural log of 5. That's not going to matter a whole lot. 1/2 times natural log of 5 minus infinity is still infinity. So basically, we get that our integration integrates to infinity. This is not the only way I could have done this, but using u substitution, it's pretty obvious. So that means this integral diverges. And because the integral diverges, the integral test says that this infinite series also diverges. So integral test tells me that this infinite series diverges. So there's no need to do a bunch of partial sum calculations because I know via integration that this thing diverges. Let's do another example. Let's take this infinite series and apply the integral test to this one. This is the infinite sum of from 1 to infinity of 4 over e to the nth power. All right, so the first thing we have to do is create a function that gives me the terms in the series. That would be 4 over e to the x if I used x as my variable. Or I'll rewrite that as 4 times e to the negative x, so it's easier to integrate. This function is continuous and decreasing and positive, and therefore we can apply the integral test. So the integral test would say, let's integrate 4 times e to the negative x from 1 to infinity. This one has a really nice antiderivative, which would be -4 times e to the negative x. So we get e to the negative x and we divide by -1. We're going from 1 up to infinity. Again, this one, I don't need a u substitution or anything. It's just a very quick antiderivative. When I take the limit as x goes to infinity, e to the negative infinity is the same thing as 1 over e to the x. So what I'm getting when I plug in infinity, again, plug in loose terminology there, meaning take the limit as x goes to infinity, you'd get a 0. And when we plug in the number 1, we'd get -4 divided by e to the first power. So when we plug in infinity, meaning take the limit as x goes to infinity, we get 0 minus -4 over e. So that means this integral converges to 4 over e. Because of the integral test, that means this infinite series also converges. However, this infinite series, while it converges, will not converge to 4 over e. We don't know what it converges to. So the integral, we know what the integral converges to. But because the integral converges, integral converges. We know the infinite series converges. However, it might not converge to 4 over e, and in this case, it definitely does not. Now, in this scenario, we use the integral test to determine that this infinite series converges. It turns out that that's not the only way we could have determined that this infinite series converges. In our previous video, we looked at the geometric test, so the geometric series test, and it turns out this is a geometric series. This is like 4 times 1 over e raised to the nth power. And starting at 1 as my sum. If I had started at 0, if n were equal to 0, then we would know that this converges to a over 1 minus r. So if I do a over 1 minus r, that gives me 4 over 1 minus 1 over e in this case, because my r is e. By the way, I know it converges because 1 over e is less than 1. E is bigger than 2. It's about 2.71828. So that's less than 1, so I know it converges. 1. So series converges. All right. So based on what we saw last time, we kind of already knew that this was going to converge. But this is another tool that we have, this integral test. Now, again, it confirms in 2 ways what we got earlier. By the way, this thing would be 4 over 4 times a fraction whose numerator is e and whose denominator is e minus 1. And then when you plug in the 0 term, you would just get 4. So what I'm saying is we know that 4 plus starting at 1, our summation starting at 1, gives me 4 times e over e minus 1. If I subtract 4 from both sides, that means my summation starting at 1 actually converges to 4 times that weird fraction minus 4. And if you rewrite that, this would be like 4 times e minus 1 over e minus 1. So if I subtract that, I actually get 4 times, this is going to be 1 over e minus 1. Again, weird formula. But my point is to say it doesn't converge to the same thing. That's the whole point. That's why I wanted a geometric one, so that we can see that while the integral test tells me that the infinite series converges, that infinite series is not going to converge to the same thing. I got 4 times 1 over e minus 1 as the infinite series, but 4 over e as the integral. So that's all I wanted to say. That is example 2. Again, example 2 shows me that the integral test tells me that they both converge, but I can clearly see that they're not converging to the same number. The integral and the infinite series both converge, but not to the same number. Now, in general, you will not have to find what these converge to if I just ask for determine the convergence. So let's take a look at this one. This is an infinite series from 1 to infinity of 1 over n to the 1.5 power. We're going to figure out if this converges or diverges based on the integral test. And then after I do that example, I'll immediately do this one. Infinite series of from 1 to infinity of 1 over n to the 0.75. So I'll do example 3 and example 4. If you want to try these two on your own, you can do that by pressing pause on the video and waiting a couple of seconds. Excuse me, if you wait a couple of seconds, I will do these both. In this case, the function that we're going to use, the f of x that we're going to use, is simply 1 over x to the 1.5 power. Which can be rewritten as x to the negative 1.5 power if we'd like. It's a little bit easier to integrate in that form. By the way, f of x is always positive when my x values are 1 and above. It's decreasing and continuous. So we're good to use f of x with the integral test. So let's go ahead and do that. I had my last integral there. So let's integrate that. The antiderivative of 1 over x to the 1.5 power is the same as the antiderivative of x to the negative 1.5 power. So what I would do is I would add 1 to that exponent. That would be x to the negative 0.5 power. And then I would divide my coefficient by my new exponent. 1 divided by a negative 0.5 becomes a negative 2. Before I put the bounds on, let me just say this. That's the same as negative 2 over x to the 0.5 power, or in other words, the square root of x. We're going to do this integration from 1 to infinity. When I take the limit as x goes to infinity, this denominator goes to infinity. So the limit of that thing is 0 when I take the limit as x goes to infinity. And then when I plug in a 1, I get negative 2 over 1 to the 0.5, which is just a negative 2. So the integration converges. It converges specifically to 2. That means, based on the integral test, this infinite series also converges. And that's what the integral test allows me to say. It says 1 over n to the 1.5 that infinite series summed up from n equals 1 to infinity converges. Now, again, it doesn't tell me what it converges to. It's not going to be 2. It's going to be a different number. But the question just asks whether or not this converges or diverges. Now, that same thing can be done with the next example. The next example, let's go on a new page here, but not erase the first one, is 1 over n to the 0.75. My function would be 1 over x raised to the 0.75 power. Or we can think of it as x raised to the negative 0.75 power. I would do an integration from 1 up to infinity. Oh, let me rephrase this. This function is continuous, always positive, decreasing. Therefore, I can use the integral test. The integral test would have me integrate from 1 to infinity, 1 over x to the 0.75 power with respect to x, again, from 1 to infinity. The antiderivative is the antiderivative of this. We'd raise the exponent by 1. If I raise the exponent by 1, I get x to the 0.25 power. And then I would divide by the new exponent. So 1 divided by 0.25 gives me a 4. I'm going to plug in 1 and then take the limit as x goes to infinity. If I take the limit as x goes to infinity, in this case, as x goes to infinity, x to the 0.25 power is going to grow and grow and grow. So when I take the limit as x goes to infinity, my function becomes infinity. If I plug in 1, my function becomes 4. Infinity minus 4 is still just infinity. And therefore, the integral diverges. Since the integral diverges, this infinite sum, this infinite series of 1 over n to the 0.75 summed up from 1 to infinity also diverges. Now you'll notice that these two series were very close to each other. One was 1 over n to the 1.5. The other was 1 over n to the 0.75. The infinite summation of those two things. So infinite summation of 1 over n to the 1.5, that happened to converge. So this infinite series converges. The infinite series where we sum up 1 over n to the 0.75, we see diverges. In the integral test, you can see the reason why. When we rewrite our function as x to a power, we write as x to the negative 0.75. In this case, when I added 1 to negative 0.75, I got a positive exponent on my x. And therefore, taking the limit as x goes to infinity brought me to infinity. On the other one, when I raise the exponent by 1, taking negative 1.5 raised by 1, I got a negative 0.5 as my exponent. So in other words, I got a negative exponent. And in that case, when you take the limit as x goes to infinity, infinity to a negative power or something over infinity to a power has limit of 0. So the crux of the matter was our exponent here bigger than 1 or was our exponent smaller than 1? Now, I went bigger than 1, smaller than 1. Obviously, there's one more option, and that's what happens if x is, or excuse me, if our exponent is equal to 1. What if we just had 1 over n to the first power? In that case, my function would be 1 over x. Again, that's decreasing and continuous and positive. When I did the integration from 1 up to infinity of 1 over x, the antiderivative of 1 over x is natural log. And sure enough, as I plug in bigger and bigger values for x, natural log of x gets bigger and bigger and bigger, although slowly. And then when I plug in 1, I get a 0. So the integral diverges, and therefore this infinite sum is also going to diverge. So if I have the form 1 over n to a power, and that power is a positive power. So if I'm adding up 1 over n to a power from 1 to infinity, if that power is bigger than 1, I know it's going to converge. If the power is less than 1, I know it's going to diverge. And if the power is equal to 1, I know it's going to diverge. Now, the infinite series that I'm talking about have a special name. And the name for those is a P series. So a P series is an infinite series of the form infinite sum from n equals 1 to infinity of 1 over n to a power, where that power is greater than 0. So it's non-zero power. If the power was negative, then we'd just be summing up n to the 1 over n to a negative power is like n to a positive power. So that would diverge. But a P series is an infinite series where the terms are given by 1 over n to the p power. And what my previous examples showed is essentially what we call the P series test. So the P series test is what we call in math a corollary of the integral test. The integral test showed us that if the power P were greater than 1, then the integration would converge, and therefore so would the series. It also showed us that if that power were either less than 1 or equal to 1, then the integral would have diverged, and therefore the series would also diverge. So the P-series test says, let's just know that now. Now that we know that, we can say anytime I have a series of this form, if P is greater than 1, I know it's going to converge. If P is less than or equal to 1, I know the series is going to diverge. This is the p-series test, and it's a fairly important test to use. Let's take a look at a few examples, and using the p-series test, we will quickly determine which series diverge and which series converge. Here those series are. So we have 1 over n to the 8th added up from n equals 1 to infinity. This is going to have to converge because it is a p-series, and p here is equal to 8. And obviously 8 is bigger than 1, therefore it's going to converge. This next series is 1 over n to the 0.2 power, that is 0.2 power, summed up from 1 to infinity. This is going to diverge because it is a p-series as well, but the p here is 0.2 or just 0.2, which is less than 1. One over n to the 3/7 power is also going to diverge. That is a p-series with a p-value of 3 over 7. And since 3 over 7 is less than 1, the series diverges. Lastly, 1 over n to the 8 over 5 power is going to converge because that is a p-series and p is 8 over 5, which is bigger than 1. So 1 over n to the power summed up from 1 to infinity, we can determine convergence and divergence very, very quickly. We can change these p-series up a little bit as well and quickly see some other series that aren't exactly p-series but very nearly p-series. We'll take a look at that in the next example. In this next example, let's say instead of summing up from 1 to infinity, we sum up from 18 to infinity. And instead of having 1 over n to the 8th power, let's say we have 2 over n to the 8th power. Or let's sum up from 3 to infinity. Instead of having 1 over n to the 0.2 power, let's now have 32 over n to the 0.2 power. Now you can probably guess what's going to happen in each of these. For both of these, having a 2 instead of a 1 in the numerator is not going to affect this much because if we do converge, we can just factor out a 2. That is the constant multiple rule. Remember, if we multiply by a constant, then we can factor it out. So multiplying by a 2 isn't going to affect whether or not this converges or diverges. It will affect whether or not what it converges to or what it diverges to. Or I shouldn't say what it diverges to, what it converges to if it does converge, but doesn't affect whether it converges or diverges. again, I can factor out that too. Also, if you think about it, starting at 1 versus starting at a count are 18 basically just means my first 17 terms are not included here. That's actually not a big deal because the sum of the first 17 terms is always going to be finite. Therefore, if it converges and then you add on a finite number of 17 extra finite terms, it's still going to converge. Or subtract off 17 terms, it still converges. So since the first 17 terms are finite, it's not going to affect whether it converges or diverges. By the way, if it diverges, then it's going to infinity. So subtracting off 17 terms from infinity doesn't change anything. It's still going to be infinity. Therefore, 1 over n to the 8th, an infinite sum from 1 to infinity, we know converges because of the p-series test. And what I'm arguing is that 2 over n to the 8th, no matter where we start, as long as we sum up to infinity, that is also going to converge. Again, you can factor out any constant number, and then starting at any value other than 1 still doesn't affect whether it converges or diverges. If it does converge, it'll affect what it converges to, but not the fact that it converges or diverges. In the same sense, if I sum up from 3 to infinity, 32 over n to the point 2, that's going to be like the p-series with 1 over n to the point 2 in the that we're adding up. P there is 0.2, therefore this is going to diverge. So the first one is like a p-series with p of 8, so we knew it converged. The second one is a p-series with a p of 0.2. It's like a p-series with a p of 0.2, so we knew it diverged. Again, p greater than 1, we get convergence. P less than or equal to 1, we get divergence. Now, what we were doing with these two is really using just logical deduction and comparing these to the p-series tests that we know. Well, we can also make comparisons in more complex sort of ways. So we want to compare a series that is slightly more complex to a simpler series that we already know what happens. So what I mean is the simpler series, I can easily figure out whether that simpler series converges or diverges. And based on that simpler series converging or diverging, then I can project that on to a more complex series and determine whether that one converges or diverges. So the case there is like an infinite sum of 1 over n compared to an infinite sum of 5 over n plus 2. We have a constant term in the numerator, and our denominator in both cases is linear. So we would expect that we can compare these two in certain ways. And in fact, we can. We are going to look at two comparison tests. We'll deal with a direct comparison test first, and then we'll do a limit comparison test. The limit comparison test is probably both of them are going to be useful, but the limit comparison test is the one that I tend to use more often. So here's what we say. Let's say we have positive sequences of numbers. So positive sequence A sub n and positive sequence B sub n. And let's assume that at some point the B's are always bigger than the A's. Well, then the infinite sum of the B's should be bigger than the infinite sum of the A's. At least if we start our count big enough. So for some n, the B's are going to be bigger than the A's. And if I start my count at whatever that number is, let's just pretend that number is 1. So B's are always bigger than the A's. Then if the series with the bigger numbers converges, then the series with the smaller numbers also converges. If the series with the smaller numbers diverges, then the series with the bigger numbers is also going to diverge. That should make sense. If these things add up, if the B sub n's add up to a finite number, then adding up smaller numbers should also give you a finite number. If adding up the smaller numbers gives you infinity, then adding up the bigger numbers should also give you infinity. So if we have this scenario, and again, these sequences both have that with the A sub n and the B sub n, those sequences both have to be positive for this direct comparison test to work. So if we have that scenario, then we're in a good spot. Let's take a look at this example. In every single example, we are going to ask ourselves, what does this series compare to in comparison to a series I already know? We've looked at geometric series so far. We've also looked at p-series. We have a really nice test for geometric series convergence. We also have a really nice test for p-series convergence. So we're going to be utilizing something that we already know and compare this series to that. Whoops. In this case, what I'm going to compare to, since this is like a polynomial divided by a polynomial, I'm going to think p-series comparison. So I'm going to compare this to 1 over n to the first power. Notice how this is a polynomial of degree 1 on top and a polynomial of degree 2 on bottom. So I'm going to compare it to 1 over n. Now that I know diverges because that's a p-series where p is 1. And remember, that was the sort of cutoff case. When p is 1, it diverges. Anything bigger than 1, it converges. Anything less than 1, it still diverges. So that's a p-series with p of 1. So that's why I know it diverges. Now, then I can do a direct comparison in this case. The terms in my original series compared to the terms in the one I'm comparing it to series. So I'm comparing 1 over n to n plus 1 over n squared. It turns out that n plus 1 over n squared is always going to be greater than 1 over n. You can see this by multiplying both sides by n squared. Uh, if I multiply the left-hand side by n squared, I get n plus 1. If I multiply the right-hand side by n squared, I just get n. So it's pretty easy to see, and n squared is positive, so that's not going to flip the sign. So it's pretty easy to see that if I multiply both sides by n squared, that the left-hand side is bigger than the right-hand side. Always. So that means I have an infinite series with smaller numbers which diverges. Therefore, the infinite series where I'm summing up bigger numbers also is going to have to diverge. So that one also diverges because of the direct comparison test. So if an infinite series summing up smaller numbers diverges, then I know that the infinite series summing up the bigger numbers also has to diverge. Let's do another direct comparison test. We'll take the infinite series 1 over n factorial. This one is going to be a little bit trickier to figure out what I need to compare it to. N factorial is a very fast growing expression. And so what I'm going to think is that a very fast growing expression in the denominator should be compared to something that I know, which has also a pretty fast growing expression in the denominator. It turns out you can use a lot of different things. You could actually use either a geometric series, you could use a p series, as long as the p is bigger than 1. I'm going to use the p series where I take 1 over n squared as my terms in the summation. So we're going to compare to that. I know that this converges because that is a p series with p equal to 2. Since p is equal to 2, that is bigger than 1, and therefore I know the p series converges. Now let's compare the terms. 1 over n factorial versus 1 over n squared. Now, if I don't see what the comparison is yet, I can always just cross multiply. If I cross multiply, I get n squared versus n factorial. And the n factorial is going to be bigger than the n squared as long as n is at least 4, I believe. 4 factorial gives me 24. but 4 squared gives me 16. The first couple of terms, when I plug in 2, actually the n squared is bigger. When I plug in 3, the n squared is bigger. But when I plug in 4, n factorial is bigger. When I plug in 5, n factorial is bigger. Anything beyond 4, n factorial is bigger. So for n greater than or equal to 4, the n factorial is bigger. That means 1 over n factorial is smaller. I have a smaller number because I have a bigger number in the denominator. 1 over a bigger number is smaller than 1 over a smaller number. Again, these two are the same inequality statements, just this one, the second one, is the one I get from the first one when I cross multiply. Now I'm ready for my comparison test, my direct comparison test. I'm using these terms, which are all positive terms. I should have pointed that out. All of these terms are positive. In my previous example, they were all positive as well, where I know the sum of the bigger terms converges. Therefore, the sum of the smaller terms also converges. So by the direct comparison test, since the sum of the bigger numbers converges, the sum of the smaller numbers also has to converge. So this infinite series, 1 over n factorial, I know is going to converge. And if we took the sum not starting at 1, if we started the sum at 3 or started the sum at 15 or multiplied by a constant, then I know all of those have to converge as well. So that's how we deal with that direct comparison test. We look at a comparison of the two series based on a direct comparison of the terms. And if the series with the smaller terms converges, then the series with, or excuse me, with the series with the larger terms converges, then the series with the smaller terms also has to converge. And on the last one, if the series with the smaller terms diverges, then we know the series with the larger terms also has to diverge. The next comparison test is the limit comparison test. Let's say a sub n and b sub n are both positive sequences, so they're both have terms which are always above 0. And that if I look at the ratio of those sequences and take the limit of that ratio as n goes to infinity, if that ratio is any non-zero real number, then both the infinite series when I sum up b sub n and the infinite series when I sum up a sub n are going to converge, or both series will diverge. So they both do the same thing as long as the ratio of the terms has limit of some real number. Basically, what this is saying is that the terms are essentially decreasing or growing at the same rate. So they are growing or decreasing at the same rate. That's really what it means to have the limit be some real number. They're growing or decreasing at the same rate, except for maybe one is a constant multiple of another. So if that happens, if the limit of that ratio is some real number, then they both converge or they both diverge. Both infinite series converge or both infinite series diverge. But we can't have one do one thing and one do the other. Let's look at this example. We have an infinite series summing up 1 over 3n squared minus 4n plus 5 from n equals 1 to infinity. I want to figure out if this infinite series converges or diverges. And I'll use the limit comparison test to do so. As always, with either the direct comparison or with the limit comparison, the first thing I'm going to ask is, what does this infinite series compare to? In this case, the best infinite series to compare this to is 1 over n squared summed up from 1 to infinity. The reason why I want to use this one is because my rational function here is 1 over a quadratic. It's 1 over 3n squared minus 4n plus 5. That's giving me the terms in the series. So the terms in the series are kind of behaving like 1 over a quadratic. And I already know that the series summing up 1 over n squared from n equals 1 to infinity, that converges because it's a p-series. In fact, I already wrote that down. And it's a p-series with p of 2. For me, this is basically all I do. And I know that these terms are behaving very similar. And so what I do from there is I just say, based on the limit comparison test, this infinite series also converges. Now, some people actually go and do the hard work of finding the limit of these two ratios. So when I say two ratios, I mean the A sub n over B sub n or B sub n over A sub n. So the arguments inside are the things that are being added up. I look at the limit as n goes to infinity of that ratio. So I'll show that here. But again, usually I just say, oh, I know these two are going to have limit that is a real number. I don't have to like go through the busy work of finding that limit. So I don't usually find the limit. I usually just say, therefore, it converges. But just for the sake of completeness, let's actually figure out what that limit would be. The limit in this case doesn't matter whether I put 1 over n squared in the numerator or whether I put 1 over n squared in the denominator. And then I'm going to put 1 over 3n squared minus 4n plus 5 in the other side of the fraction. If I do that, then what happens is I could multiply by the reciprocal of this denominator, that would give me a rational expression of 3n squared minus 4n plus 5 divided by n squared. That's if I multiplied by the reciprocal of this denominator. Notice that that limit, since I have n squared over n squared, that limit is just 3. So the ratio between the terms in one series and terms in another series as n goes to infinity is equal to 3. And that shows I could have used my limit comparison test. By the way, if you would have flip-flopped your numerator and denominator, instead of getting a limit of 3, you would have gotten a limit of 1/3, which would have told you the same thing. 1/3 is still a real number that's not 0. And so we can use the limit comparison test. If this one converges, so does this one. Again, a lot of times I skip this step of finding what the precise limit is in favor of just uh, shortening the time, I guess, that it takes me to do the problem. But if you do need to show that you can use the limit comparison test, then you'd find that limit. And in this case, that limit would be 3. Or 1/3, depending on which one you wrote in the numerator and which one you wrote in the denominator. Let's do another example. Let's take the infinite series of summing up 1 over the square root of quantity 5n minus 2 from n equals 1 to infinity. In this case, as always, I'm always going to ask first, what should I compare it to with the limit comparison test? Well, in these cases, when I'm using the limit comparison test, I say, what do I compare this to? I want a simpler series where I know what's going on. And it takes a little bit of time getting used to, but really not much time. You see, hopefully, this is a ratio, and you start saying, well, as n gets really, really big, this minus 2 isn't going to matter a whole lot. And this 5 in front of the n, well, that can actually be factored out if I want it to. So let's factor it out and then ignore it. And then I'm left with a 1 over the square root of n, which is the same thing as 1 over n to the 0.5 power. That is a p-series with a p of 0.5. That is less than 1, so that series diverges. Through the limit comparison test, therefore, we know that our series is also going to diverge. Now, we may say, can we be sure that our series has limit comparison to this series? It turns out, yes, we can. If you want to confirm that, then you just actually find the limit of the ratio between the terms as n goes to infinity. So I'll do that. Basically, what I have is, what is that now? A limit. Doesn't matter which one I put on top and which one I put on bottom. I will put the 1 over the square root of n on top. And then on bottom, I'll put the 1 over square root of the quantity 5n minus 2. If I flip and multiply, I'm going to get the square root of 5n minus 2 divided by the square root of n. Take the limit of that, and basically you get the square root of 5. I won't go through all the steps. You could, rewrite this, and you do lots of different things, but it's the square root of 5 as it comes out. If you want to use L'Hopital's rule, if you want to use some other algebraic techniques, that's perfectly fine. Basically, you just factor out a square root of 5 from the top, and then you get a 1. So square root of 5 is that limit. Square root of 5 is a non-zero real number. So that means that these infinite series are either both going to diverge or both going to converge using the limit comparison test. Again, a lot of times I just ask myself, what do I compare this to? I write that down. I say that thing diverges. Therefore, the one I want to find is also going to diverge. And I skip the confirmation of the fact that the limits become a real number. I know it kind of in my head that that's going to happen. And so I might not write down this process. Like I said, the limit comparison test is something we'll use quite often moving forward. So we're going to do a few more examples with the limit comparison test. If you want to try this example 11 on your own, go ahead, push pause on the video. In a couple of seconds, I will show how to do it on the computer. In this situation, I want to compare this infinite series to the P series where I sum up from 1 to infinity, 1 over n to the third. The reason I'm choosing that is because I have an n squared in the numerator and an n to the fifth in the denominator. So as n grows and grows and grows, that's going to behave like n squared over n to the fifth, which reduces to 1 over n to the third. So again, n squared over n to the fifth, those are the highest growth terms. And that reduces, when I do my exponent rules, to 1 over n to the third. I know that converges because that is a P series with P of 3. And therefore, as long as these have the same growth, which I know they do, this infinite series that I'm given also converges. The n squared minus 5 divided by quantity 7n to the fifth plus 18, summed up from 1 to infinity, also converges. Again, that's what I tend to do. I leave it at that. But obviously, if we wanted to confirm that we got what we were looking for, I just take either my original series divided by 1 over n to the third, or 1 over n to the third divided by my original series. If I do that, when I multiply n to the third on top and multiply 1 in the denominator, so in other words, multiplying by the reciprocal of 1 over n to the third would give me n to the fifth minus 5n to the third on top. And in the denominator, I would get 7n to the fifth plus 18, which is polynomial over polynomial of the same degree. Therefore, I can pull off the coefficients. As n goes to infinity, that ratio goes to 1/7. By the way, if I would have flip-flopped which one's on top and which one's on bottom, then the limit would have been 7. That's a real number, which is non-zero, and therefore both of these are going to converge. That is how we do the limit comparison test in this example. Again, most of the time when I'm going through a test, I tend not to write this all down. I tend to just say, oh yeah, that is like 1 over n to the third type growth/decay. That's behaving like 1 over n to the third. Let's do another example. And as always, if you want to try this on your own, feel free to try this on your own. In this example, we have a series which is 1 over, and in the denominator, we have n times the square root of n squared minus 2, summed from 1 to infinity. Actually, let me pause on this a second and say this actually wouldn't be a good one to do, because when I plug in 1, I get a -1 underneath a square root, which doesn't make sense. So instead, let's say that we started with n equals 2 so that we didn't have any trouble in this denominator. So there, we fixed it. Infinite sum, starting at 2 this time and going to infinity, of 1 over the denominator of n times the square root of n squared minus 2. You'll see that sometimes when your count doesn't start at 1. And sometimes the reason for that is just that we want to avoid having a troublesome spot when I plug in an n of 1 or whatever other numbers. So let's do this problem. In this case, 1 over n times square root of n squared minus 2. What I do is I'm going to tend to think about that starting at my count at 2. This minus 2 isn't going to do much when we get really, really big, when we get close to infinity. Square root of n squared is just an n. So I get n times n in the denominator, which is just like n squared in the denominator. If I'm going to do this comparison, then I'm going to use that as my comparison. Now that is a p-series with p of 2. Obviously, we start our count at n equals 2 rather than 1, but that's not going to affect anything as we saw earlier. This p-series, since p is 2, converges. I know in my head that the limit between these terms and these terms is going to be a real number that's not zero. So I know my infinite series also converges. Now, if I want to show that the limit of the terms is a non-zero real number, I can absolutely do that. I can take these terms, I'll put those on top, my given terms on top, and then 1 over n squared on bottom. When I multiply by n squared over 1, multiply the numerator by n squared over 1, I get n squared over n times the square root of n squared minus 2. The limit of that as n goes to infinity, well, I can cancel out one copy of n on top with one copy of n on bottom. It's pretty easy to see that that's going to be 1. If you don't see that, then you can obviously take a derivative. You can use L'Hopital's rule is what I mean. So take a derivative of the top, derivative of the bottom. You can do some other things as well. But L'Hopital's rule would probably be the easiest to see that that limit is 1 if you can't deduce that by just looking at this ratio. So anyways, 1 is a non-zero real number, and therefore the limit comparison test works. Therefore, since this p-series converged, the series that I wanted to find also converges. I'll do one more example of the limit comparison test. Let's take an infinite series where we're summing up in the numerator n squared plus 7n, and with denominator n squared minus 2n plus 10. Summing that up from n equals 1 to infinity. All right. Now, as n gets really, really big, it's going to be, the numerator is going to be dominated by that n squared term, and the denominator is also going to be dominated by that n squared term. When I cancel things out, I get a sum of just 1. By the way, that's a constant series, and this diverges based on what we saw in the last video, which was the divergence test, which said that if these terms don't have limit equal to 0, these terms in fact have limit equal to 1, then there's no way that, or I'm sorry, it wasn't the divergence test, the divergence rule, excuse me. The divergence rule said if the limit of the individual terms doesn't go to 0, then summing them up is going to lead to an infinite sum, and therefore the summation is going to diverge. That's also pretty obvious that if you just take 1 plus 1 plus 1 infinitely many times, it's going to go off to infinity. So that's the divergence rule. Now, I know that this infinite series is going to behave like this infinite series. So by the limit comparison test, the infinite series that I was given also has to diverge. This one is real easy to see. If I had to show that I can use the limit comparison test. I just take the terms from my series, divide by the terms from the series I'm comparing it to. That's just dividing by 1. And so we get the limit, which is 1, which is a non-zero real number. So I can use the limit comparison test because the ratio is a non-zero real number. Therefore, since infinite series where I'm summing up 1 diverges, then the infinite series that I'm given also diverges. I wanted to do at least one that wasn't comparing it to a P series because most of the examples we did compared to a P series because we knew that already. We knew the convergence and divergence of the P series. So this is one where the limit comparison test is to a series which is of constant numbers, adding up a bunch of constant numbers. Now, once you've seen the limit comparison test, that is something people tend to do over all of the other tests, if they can. Like earlier in this video, we did an integral test on an infinite sum of n over n squared plus 4. And when I did the integration, I had to use a u substitution, but it came out as infinity. And so we knew that this infinite series diverged because the integral also diverged. That corresponding integral also diverged. But I had to use a substitution to actually figure this out. Well, now with the limit comparison test, I can simply say, take that infinite sum and compare it to an infinite sum of, well, this is linear over quadratic. So think of this as 1 over n to the first power, which I know based on the P series, P there is 1. That's going to diverge. And therefore, my series also diverges based on the, again, limit comparison test. So that's actually a very quick way to figure out divergence and convergence if my series can be easily limit compared to a series I already know using the limit comparison test. So if that happens, then the limit comparison test is really, really nice. And I don't have to do all of this integration. So what I'm trying to point out is that the limit comparison test is a really efficient test if it can be used. Now, I mentioned the fact that this works, the limit comparison is really efficient if it can be used. So I tend to use that one if I can. However, there are some infinite series where the limit comparison test is not going to be able to be used very effectively. For instance, if I didn't already do this problem and I wanted to figure out if the infinite series where I sum up 1 over n factorial from n equals 1 to infinity converges or diverges, the limit comparison test wouldn't be very good. The limit comparison test, I wouldn't have anything that has the same limit, when I take the ratio of 1 over n factorial to the ratio of some other with some other term, that other term would have to have a factorial in it. And since I don't have a test with factorials, the limit comparison test would not have worked here. Now that we've used the direct comparison test, we know that infinite series converges. So moving forward, I could use this. I could use this series because I know it converges. But if I had not known that to begin with, I couldn't use a limit comparison test on this one. But my direct comparison test worked, and now we know that the infinite series converges. That's what this section was all about. This section was about trying to create easier ways to find out when an infinite series converges and when an infinite series diverges. And now we have a few different methods for that. We have the integral test, we have a direct comparison test, we have a limit comparison test, and now we know about when P series converge and when P series diverge. We also know when geometric series converge and when geometric series diverge. And so that is the end of this section.